Just be record to the cloud. All right, um, so here's what we're gonna do. So um, when we do a plot of W with some spectra, right? Oops, what's going on here? Oh boy, what's going on? With some spectra, so we have S, lambda, and then we have our little thing. So you can also, in fact, this is omega. So we can convert this to a velocity scale so that you can plot V and S, V in velocity scale. Well, what does it mean? So it means if you recall your Doppler effect thing, so del lambda over lambda is equal V over C. So for a given wavelength scale, so let's say if we choose 6,000 angstroms um, uh, as our reference point in the spectra, then the new velocity scale would be c speed of light that multiplies c lambda minus 6,000 divided, in fact, yeah, divided by 6,000. So we have something like that, right? And all of that multiplying. So basically, your new velocity scale would be given by this quantity here. And lambda is your wavelength scale, if that makes sense. Now, if you want to play out with some shifted spectra, I could create a new spectra, kind of a fake one, that is shifted 50 kilometers per second. So let's say if we want to shift a spectra 50 kilometers per second, so in velocity scale, we would have V and S. It would be the same thing. It would appear kind of the same spectra as I showed before. And if we want to shift it 50 kilometers per second, now the new scale, sorry, the new scale in velocity would be the old one, V, plus 50 kilometers per second, right? And then if we plot, well, I will use the same curve. Do I have color? I think I do. I don't know. Do I have color? No, that's not it. Do I have color? No. I don't know this software well. I don't know where I get color. So let's go back there. So is it here? Favorite color. Oh, there you go. Color. So let's choose this color here. Okay, that's good. So then, so in a new scale, so if we were to plot S by this new scale, it would appear like this. See, there is a shift. Right? Shit. Not here. And if you check this shift over here, they are both 50 kilometers per second. Okay. So going back now, um, to sharing my screen. So I'm gonna do exactly that. So I I call here a template. By the way, I was trying to tape before and got all crazy here. So I call the spectra, the solid spectra, which is WT at sun, and I'm cutting in 40 angstroms and loading that in WSSS, right? And then I'm cutting this WSSS in, oh, I already cut it. So I'm plotting that, and uh, and then you have these nice lines over here, right? So just memorize them. So what I'm gonna do is create this velocity scale. So V is equal the speed of light, that's round to 300,000 kilometers per second, divided by 6,000, and I'm putting that in 6,000 angstroms, times the old scale, WT, minus 6,000, okay? And then what I would do, I would plot V by SS, and it should appear the same. Okay, wait a second. XR, XL. What's going on here? Ooh, 6,000. Oh, I did something wrong here, sorry. That would be 6,000 better. Okay. 300,000 kilometers per second. Tall and Giselle. And then what I thought. Why am I getting this crazy thing here? SSS. Okay. Okay, WT. It's not WT, it's WS. Okay. Now let's do that. Oh, no. VWS. Okay. So now we have the same spectra we had before, but now in velocity scale. So that. So this region here at zero corresponds to 6,000 angstrom. Okay. Now let's shift this 50 kilometers per second. So I'm gonna plot overplot. No, not WS. Overplot V plus, just to make it so aggressive, let's go to 100 kilometers per second. V SS, and let's put a different color. Color is equal 150. So now you have the spectra entirely shifted. Okay. Now, in velocity scale, if you go with the cursor and you measure, for instance, point, let me see, if you go point VSS A B, and then you do it again, VSS A B, A1 and B1 maybe, a print A1 minus A. So what I'm doing is I'm gonna, with a cursor, I'm gonna click on two of these line centers and see the difference between them. Okay. There you go. So let's say I'm gonna take this point over here and this point over here. So it's 95 kilometers per second. So I have some error there. So if I do it again, let's say between this and that one. Again, this is not precise because I'm not expanding. That's 98. So you have the same wave, the same scale, right? Now let's do one thing, because when we do the radial velocity correction is we select a certain region that has a good set of good lines that you can trust them. It's not telluric lines, not nothing. And then you compare your spectra, let's say the red one, which is Titori, you compare with the sun and see they are not matching. So what you do? You convert both of them, not a wavelength scale, but you convert both the sun and the Titori to velocity scale. So their wavelength is not wavelength anymore; it's a velocity. Okay, like I just did. And then you use either cross correlation or a Fourier transform, um, but basically cross correlation works fine. You start essentially what you do. You keep moving the red spectra right and left certain amount of pixels, and you multiply both the spectra. Basically, that's what we do. And so certainly when there is a perfect match is when the multiplication is going to reach the maximum value. Okay, and then after this matching point, the multiplication is start falling down, and then you know how many kilometers per second there is between your template, your target, your whatever, and your standard spectra. In the case I'm using the sun. So when you find how many kilometers per second it is, in the case of TW Hydra, we found 13 kilometers per second. So when you find that, um, then you do the other way around. You go back to the wavelength scale of your, and that's what I did, by the way. But there are different techniques. One technique is to use a Fourier transform, and then you shift your spectra, knowing that you have to shift, let's say, 13 kilometers per second, or in my example here, 50 kilometers per second. You shift the S. You shift the spectra itself, or you use what I did. I just convert the wavelength. I shift my templates in the TW Hydra. I shift in velocity scale to, let's say, whatever it had before, minus 13 kilometers per second. And then once I've done that, I convert that back to wavelength scale. So the shift, what I'm trying to say is when you do the shift must be done in velocity scale, never in wavelength scale, because your wavelengths shift. Let's say if you go in 6,000 angstroms and you determine with precision the shift between two pixels that have line. Let's say you are going to measure a shift of 0.2 angstrom to the right, and then you convert 0.2 angstrom to a certain velocity scale. Now, if you go now not in 6,000 angstroms, but to 8,000 angstroms, and you do the same exercise with two lines that you know they are good bona fide lines, you're not going to find 0.2. You're going to find some different value in wavelength because, again, the shift is done in velocity. I don't know if this helps you or not. Once you watch this tape, we can talk. I will be in the computer. I'm working back, trying to get my week going because this weekend was a disaster as far as academics concerned. But let me know, and we go from there. Okay.